morning. So, we are going to continue our discussion on neural network for pattern recognition. So, firstly I will just briefly go through what we have done in our last class, then we will proceed further. So, in the last class we have talked about a single layer, single output neural network, where when I say it is single layer, basically there are two layers. One of the layer is the input layer, and the nodes in the input layer are simply used to connect the feature vectors. So, the purpose of this input layer node is whatever is inputted to the input layer nodes, those nodes simply forward that input to the layer above it, okay. And those inputs get weighted by the corresponding connection weights connecting the input layers to the layer above it and summed up at the next layer, and on top of that you apply some sort of non-linearity. So, effectively the single layer, single output neural network we have said was something like this, that it has a number of input layer nodes. So, this is the layer which is input layer. So, the number of nodes in the input layer is same as the dimensionality of the feature vectors plus 1, which is used to take care of the bias or the bias weight, okay. And the number of nodes in the output layer in this case will be only 1, which will indicate either one of the two classes, okay. So, if the output of the output layer node is greater than threshold, in which case the output of the output layer node will be set to equal to 1, which will indicate say class 1, and if the output is 0, it will indicate class 2. So, the connections that we will have is something like this. So, here I have x 0, which is usually set to 1, and the connection weight over here is W 0, which takes care of the bias weight. Whereas, the other inputs will have the different feature components x 1, x 2 up to say x n, and the corresponding connection weights are W 1, W 2 up to W n, okay. And output of the output layer node, which let us say that this output is equal to D, okay. So, this is my output layer node, okay, where D will be equal to the weighted sum of the input feature vector components. So, it will be simply summation of W I x I, where I varies from 0 to n, okay, where n is the dimensionality of the feature vector and x 0, which is usually set to 1, that is to take care of the bias weight, okay. So, then what we said is, while training the neural network, we have to decide these connection weights, or what will be the weight vector that will classify the unknown feature vectors between one of the two classes, say class omega 1 and class omega 2. Okay. Now, while training, because all the feature vectors which are given, we know what is the class belongingness of those feature vectors. So, we effectively know that what is the expected output. Okay. So, if I take a training sample, a training feature vector, which we know that the training feature vector belongs to class omega 1, we know that the corresponding output has to be equal to 1. Or if I know that the feature vector belongs to class omega 2, then it is known that the corresponding output has to be equal to 0. So, for the training samples, for each of the sample which is presented to the neural network, we know what is the corresponding output. Okay. And because initially the weights are not set properly, because we start with arbitrarily set weights of very low values. So, even if our training sample which belongs to class omega 1 is given to the neural network, the output may be 0 or output may have any of the continuous values between 0 and 1. Okay. So, it may not be equal to 1. So, what is the expected output and what is the actual output that you get, the difference between between these two is the error. Okay. So, if I say that my actual output that I obtain after giving a training sample, after inputting a training sample is given by the expected output is say D, and the actual output that I get D, capital D, which is nothing but this summation W I x I varying from 0 to n. Okay. Then the difference between